So, in the last lecture I gave you a very exotic use of lasers, that is in the inertial confinement fusion research, and there I spoke about the nuclear fusion process and how humankind, man or scientists, they are trying to produce all the processes that are happening in the sun and the stars, unlimited kind of energy from there, and all because of the fusion process which is taking place there. And we scientists want to convert, bring about a little bit of the sun on this earth. Okay. So, we saw that if the number of nucleons is less than 56 within a nucleus, 56 refers to iron, then an increase in implying nucleon, then the binding energy per nucleon increases if A is less than 56, and if A increases implies fusion of lighter nuclei into heavier ones. Okay. So, the standard is iron. Okay. And then we came to the Lawson's criteria, a very important criteria which describes when and how fusion will take place, in a lab. So, I had described eta tau is equal to 10 to the power 14 per centimeter cube second. Okay. And the time, that is the tau, for which the electrons, not electrons and ions, the ions come close together, they should at least remain for 0.1 seconds in order for the fusion to take place. But this is in case of a plasma with a plasma density of 10 to the power 15 ions per centimeter cube. Suppose it is a laser which is hitting a target, then the time scales we are talking about are in femtoseconds, and the density we are talking about is in terms of 10 to the power 23 ions per centimeter cube. And all this is comes from the Lawson's criteria. And because of this criteria, which is a stringent criteria, so it places stringent conditions on the laser itself. The choice of parameters like wavelength, intensity, pulse length is essential for energy absorption by the target pellet. Okay. So, and I had shown you this picture, which is actually the laboratory at a National Ignition Facility in USA. So, just to give you an idea of how big these laser systems can be. Okay. So, and as it grows bigger and bigger, it's more and more difficult to manage it and manage the different parameters that arise, and that is what I will try to describe today. So, what we have is a master oscillator power amplifier system, okay. MOPA, M-O-P-A, MOPA chains. This is a kind of architecture of the laser system which has been developed over the years in order to extract or in order to produce higher gains, much higher gain or much higher power or much higher energy than that which comes out of a simple oscillator. Okay. So, generally it consists of, you will have an oscillator which is which gives out a seed pulse like this, okay. And the laser is travelling along these blue arrows and then goes into the first amplifier. After that, that pulse, the same pulse which has been amplified a bit, goes into the second amplifier, gets amplified a little bit more, goes into the third amplifier and gets amplified to a large extent like this. It is really a very simplistic schematic diagram, but that is the idea of a MOPA chain or a MOPA architecture of laser. Okay. So, we start off with a seed pulse which does not have much energy or intensity or power, however you can describe it, and you know the conversions from energy to power to intensity, all those. So, you have the seed pulse, and then you have this amplified pulse with a larger energy. So, this is what we are looking for. We need an amplified pulse, because the pulse that is coming out of the oscillator does not have enough energy for our purpose. Okay. So, as you can see here, just schematically I have shown that each time the amplifier gets larger and larger. Okay. Amplifier 1 is small as compared to amplifier 2 as compared to amplifier 3. Okay. The third one is the largest. So, I have just shown 3 here, but it does not mean you stop at 3. You go on increasing the number of amplifiers depending on the kind of energy that you need, how much energy that you need. Okay. So, this is in short MOPA, it is called MOPA. Now, in case of fusion, there are two kinds of laser systems or laser chains or MOPA chains that have been developed over the years. One is the carbon dioxide laser chain and one is the ND glass laser chain. Okay. Now, in case of the carbon dioxide laser chain, it has certain advantages. ND glass also has certain advantages. Finally, for the ICF process, inertial confinement fusion process, the ND glass laser chain has become more popular, and so most people, it has a lot of advantages, and that has become the popular laser chain to go for. But then still you must know what are the advantages and disadvantages of each of these chains. Okay. So, in case of carbon dioxide laser, the advantages are, it is easy scalability of the amplifiers. Okay. What do I mean by easy scalability? That means you can make larger and larger amplifiers. It is not too difficult a task. Generally, most of these amplifiers, in case of a carbon dioxide, works at atmospheric pressure. Okay. So, you can have larger and larger amplifiers filled in with carbon dioxide, CO2, N2, helium, as if you recollect my previous lectures on CO2 lectures. So, it is a mixture of gas, CO2, N2, helium, and if you modulate those ratios of these, depending on that, you will get a good glow discharge or not such a good glow discharge, and a glow discharge is important in order to get good lasing action. And these ratios you can sort of manipulate a little bit in order to get more power, less power, or adjust the pulse length, and all these kind of things can be done. Okay. So, the scalability is good because all you have to do is make a larger vessel, put in these 3 gases and pass the laser through and amplify it. Okay. So, it is quite easy to scale it up. Okay. So, that is why the CO2 laser was taken up for this process. Now, the next advantage is its efficiency, which is 10%. Okay. The efficiency, by efficiency I mean the conversion of electrical power into the lasing power. Okay. So, in case of carbon dioxide, it is a pretty efficient system as far as that goes. Now, what are the disadvantages? Disadvantage is that less effective energy coupling to target, because it is a long wavelength. When the wavelength becomes longer, it is very difficult to focus it to a tiny spot. Okay. You will get a lot of airy patterns when you focus it because of diffraction, and it is difficult to do it with a long wavelength. This is like this is from any optics phenomena itself. So, the long wavelength 10.6 micron of a carbon dioxide laser is not that acceptable, because you can't focus it. Okay. So, if you can't focus it properly, there will be less energy coupling onto the target, and remember that the target is very tiny. Okay. The target is not more than 1 mm or in that range. Okay. So, this becomes a disadvantage for the carbon dioxide laser. What about the ND glass laser? ND glass laser is, so ND glass laser is, the glass is the base and neodymium is doped in that glass. Okay. So, ND glass laser chain, advantage is it has a shorter wavelength. Okay, that is a very big advantage, 1.6 microns. Okay, that is the shorter wavelength. So, that focusability is very, very good. So, it has more effective energy coupling onto the target. Okay, more effective energy coupling. In fact, this shorter wavelength can be frequency tripled into UV wavelength. Frequency doubled and then frequency tripled. Frequency doubled, remember I had told you that ND glass with KTP crystal, you can frequency double it to the green region, double it once again, you will come close to this UV wavelength. So, UV wavelength is a very short wavelength, ultraviolet. Then it will be very easy to focus it onto your target, and there will be effective energy coupling. Okay. But what will happen is that each time you are taking a different crystal to frequency double or frequency triple, you are losing out on a bit of energy over there in that process. So, there is a slight disadvantage even in that. Okay. You are losing out on energy that you have taken so much trouble to amplify and come to. Okay. These are just things to be thought about. Then what are the disadvantages of an ND glass? Scalability of amplifier is not easy. Scalability in case of carbon dioxide was easy. In this case, it is not easy, because first of all, you have to make these very large rods or crystals. ND glass, of course, is not a crystal, but then you have to make these substances uniform and perfect in shape, size, and consistency within. So, these are large amorphous crystals, I should say, which you have to build. It is not as easy as putting gas into a vessel, into a larger and larger vessel. Okay. And then sometimes you can't even grow these crystals into a very large size. There are limitations on that. Okay. So, scalability in case of neodymium glass is not that good. And okay, another very big disadvantage is efficiency is 0.2%. Just compare it with that of carbon dioxide, which is 10%. Okay. Efficiency, that means conversion of electrical power into the laser power. Okay. So, in case of ND glass, so these are the advantages and disadvantages, but finally ND glass nowadays has become the most popular, and I will more or less stick to that. But then one cannot give up on the CO2 laser chain, because really if you see fusion, a controlled fusion and a break-even kind of fusion has not yet been achieved. You never know when carbon dioxide laser might become more important than ND glass. And a lot of research has been done on the plasma with carbon dioxide laser chains, and the plasma instabilities have been studied with long pulses of the carbon dioxide laser. Okay. So, it has its uses, and many of the physics behind this laser plasma interaction has yet not been discovered fully. Okay. So, both are there, but ND glass has become more popular now. Now, let us go to the next part. Now, here you must understand how the pulse propagates through the amplifier. Okay. The amplification process is not very much different from what happens in an oscillator, which I described before in my previous lectures. But there are still certain differences between them, certain other parameters that have to be taken into consideration. Okay. When we think of amplifying this seed pulse, the oscillator pulse, through these amplifiers. So, one very good theory which has been used for a long time and it's still being used is the Franz-Nordwig formula. It's used to describe the pulse propagation through a gain medium in amplifiers. Okay. So, Franz-Nordwig, they are two authors actually, and they gave their theoretical understanding of this pulse propagation through amplifiers way back in 1963, 64, somewhere around there. They gave this, but then it is kind of a cornerstone in the theory of pulse propagation through amplifiers. There have been lots of modifications. People have modified it to their system, but it is a still very useful formula to understand the propagation. So, the formula is described by this: E out is the output energy, and E sat is the saturation energy. Ln is of course this log, and exponential E I in upon E sat. Okay. E I in is the input energy, that means the seed pulse energy, okay, and this is the saturation energy, and then e to the power G0 L minus 1. So, G0 actually is the small signal gain. Okay. So, G0 is the small signal gain, that means G0 is sigma n. N is the population inversion, that you know, because the gain will obviously be proportional to the population inversion, which, and now one thing that Franz and Nordwig assumes is that the population gain in the medium is already achieved. You already have a population gain, a population inversion, sorry. You already have that. It's not that you're starting with the pumping and then creating a population inversion and then, so this formula is applicable after the population inversion is achieved. So, G0 can also be described as a initial small signal gain. Okay. So, initial small signal gain. So, it is proportional to the population inversion here, and sigma stands for the stimulated emission cross section. Okay. Again, it's like a probability. Cross section, as you know, it's always a probability that the population inversion will be utilized for the gain of the lasing medium. Okay. So, this is quite a famous formula. Okay. Now, the conditions are this. This is the understanding of the amplification process in realistic scenario where saturation effects limit the overall gain. I will just talk about what is the saturation effects, because here I bring in E saturation also. So, it is this formula is applicable to all realistic amplifiers. Okay. Now, what is the practical importance of such a formula? Why do we need to know this? It's used very widely to design a laser amplifier system before you make it, the design. Then it characterizes the gain of the medium, and what you can do is you can do some optimization for energy extraction. Your main aim is energy extraction. So, you can optimize the system with the help of this formula, design your laser in such a way and characterize the gain medium so that you get the best extracted energy. Okay. So, it basically describes to you the propagation of the pulse in this lasing medium when population inversion is already achieved. Okay. Now, so that is what I say here under unperturbed population inversion. That means population inversion is perfect for that system, and the amplification you will get then is exponential, because here you see this is an exponential gain is there. So, you will get an amplification which is exponential under this condition. Gain medium begins to saturate. Now, this is what needs a little bit more of understanding. When I say saturate, that means as the pulse is going into the medium, it is extracting the energy. That means your population is coming down. Okay. So, the gain also comes down. The population from the upper level to the lower level is coming down. It is being used up, and because of that the gain also reduces. Okay. So, the gain kind of saturates. You are not able to extract more energy from it, from the system. Okay. That is what is meant by saturation due to depletion of population inversion. Okay. Here I say that. Saturation effect strongly limits the gain experienced by the pulse. So, that is obvious. The population inversion comes down and the gain also reduces automatically. Okay. Here what he has done is he has given you one effective gain also here, G effective. G effective is equal to G0 1 plus E I in upon E sat. So, this defines even the gain. Okay. So, G0 is your initial gain, and G effective is after a pulse has gone in and taken out certain amount of energy. Okay. E I in upon E sat. Okay. E saturation. So, you just see here, suppose E I in, while it is extracting all that energy, suppose E I in becomes equal to E sat. Okay. So, this becomes 1 plus 1, 2. So, G effective is G0 by 2. That means your effective gain has reduced to half. So, you are talking about that energy which reduces your gain to half that of the initial. That is meant by E saturation. It is that energy which reduces the gain to half of its original one. Okay. And this happens as the lasing pulse. I am talking about pulsed lasers only, because that is what is used in fusion. Okay. So, this pulse, as it is travelling through the medium, it is extracting energy, but wherever it is depleting that energy also as it has passed through. So, so the front part of the pulse may see a larger gain, while suppose I were to, this is the pulse. Okay. So, this part of the pulse, this is the front part, front because t is equal to 0, this is time, and this is in arbitrary units. So, this front part of the pulse has depleted the gain, and this part of the pulse, say this part, does not see as much gain as this front part had seen. Okay. So, this later part of the pulse is seeing a much lesser gain. Okay. And so, it cannot extract as much as this part. That is what is defined by G effective. Okay. So, Franz and Nordvik defines this G effective, and also that energy output in a realistic system. Okay. The idealistic system is where the gain just does not deplete at all. Okay. The gain just, it remains as it is for all the pulse, for the full length of the pulse. Okay. Whatever this part sees, this part is also seeing the same, this part is also seeing the same, and this is also seeing the same thing. In reality, when you are designing lasers, now you do a lot of modeling in these kind of lasers, where suppose you have a gain medium, this is a gain medium, and you divide it into small strips. Okay. Small slips. So, this and you divide your laser pulse also into small strips. That is what is done. So, in this small strip, this is acting with this small strip, okay. And then this goes ahead to the next strip. But when this second strip comes here to the first strip of the medium, it sees the same gain, it sees a gain of G0, because this part of the pulse, it is a tiny energy which is a small signal, that is why it is called the small signal gain. When the signal, that means your seed pulse is small, then what is the gain? That means the seed pulse has not perturbed the gain at all. So, when the next part comes, it sees the same gain as G0. It is kind of the unperturbed part of the pulse, and that is how this, with a lot of computation nowadays, this has become very, very easy. So, and then you get the final output because of this. But the real case is, and if you can, you make this G effective, you introduce it into your code or into your formula, so that it works in a loop, and then you get the final output pulse and output energy. And what it does is, this also changes the shape of this pulse. This whole pulse propagation process, your pulse length has changed, its shape has changed, because each part of the pulse is seeing a different kind of gain. So, I will go ahead and we will see how this formula, but then how this formula is useful in designing a whole big laser chain. It is a starting point, and you have to tweak that design, but this gives you a first initial start.